Welcome to The Explainer. Today, we're diving deep into the world of AI, but not in the way you might think. We're looking at its role in one of the most high-stakes decisions imaginable in medicine. Who gets a life-saving organ transplant? I mean, just think about that for a second. It's the ultimate ethical tightrope. You have a very limited supply of organs, and you have to decide who gets a second chance at life. That's a decision with unbelievable complexity and immense pressure. So, to try and navigate this incredible challenge, hospitals are turning to a new tool: artificial intelligence. The hope, of course, is to bring some objectivity, some data-driven precision to a process that is just unbelievably difficult. But as you can imagine, this brings a whole new set of questions and, well, a whole new set of risks to the table. Okay, so let's get right into it. To really understand why we'd even think about turning to AI for this, we first have to understand the system it's trying to improve, and more importantly, where that system falls short. For years, the gold standard has been something called the MELD score. It's basically a formula. It takes a few key lab results, things related to your liver, your kidneys, your blood, and it spits out a number. The higher that number, the higher your risk of dying in the next 3 months, and the higher you go on the transplant list. It was really designed to make the process as objective as humanly possible. But here's the thing. A few lab values just can't tell the whole story of a patient. The MELD score might not fully capture everything else that's going on with someone's health. And simple things, like a typo in entering the data, can have absolutely life-altering consequences. This gap, this imperfection, is exactly where the promise of AI comes into the picture. All right, so you've decided to build an AI model. What's the very first step? You have to feed it data. A massive collection of patient histories that will literally become its entire understanding of the world. But this is where the first and often totally invisible risks start to creep in. So the model gets this huge diet of information. You've got the MELD score, of course, but also much more detailed lab values, how long a patient has been waiting, and something called comorbidities, other conditions like diabetes or heart disease that can have a huge impact on survival. And then you add the patient's location. Now, you might not think twice about location, but there's a hidden danger there. Is the patient in a big city or a rural area? Do they have easy access to top-tier medical care? These things can easily become proxies for socioeconomic status. And if you're not incredibly careful, the AI won't just learn to predict medical outcomes. It will learn to replicate the systemic inequalities that already exist in our society. Now, before the AI can learn anything, all that raw data has to be cleaned up. And this involves some really crucial steps. You have to handle missing information, which basically means making educated guesses to fill in the blanks. You also have to deal with outliers, data points that are way outside the norm. And finally, you standardize everything, putting it all on the same scale so it can be compared fairly. But even here, there are big risks. What if that outlier you decide to remove actually represents a real patient with a very rare but incredibly severe condition? By cleaning the data, you might accidentally erase the very people the model needs to learn how to help the most. Every single step here is a judgment call, and everyone has real-world consequences. So we've got our data prepared. Now, how do we actually teach this machine to think? This isn't magic. It's a really careful process of training, tuning, and testing. And this is the stage where the model's core logic is really forged. The first thing you do is split your data into 3 piles. You can't use it all at once. The biggest pile is the training data. That's the textbook the model learns from. Then you have a smaller pile, the validation data, which you use to fine-tune its performance. And the final, untouched pile is the test data. That's the final exam. It's how you see how the model will perform on brand new patients it has never, ever seen before. Training an AI is a lot like walking a tightrope. If your model is too simple, it might just lump all patients together and miss the crucial details that make one person more urgent than another. But, and this is a big but, if it's too complex, it doesn't actually learn patterns. It just memorizes the training data. We call that overfitting, and it means the model is completely useless when it finally sees a new, real patient. So this brings us to a really crucial distinction. Parameters are the things the model learns on its own, like how much weight to give the MELD score versus waiting time. But hyperparameters, those are the rules of learning that are set by the human developers. They define how the model learns. And getting those hyperparameters wrong doesn't just make the model a little less accurate. It can fundamentally warp its entire sense of medical priority. Finally, it's test time. We use metrics like precision and recall. Now, precision asks, of the patients the AI flagged as urgent, how many actually were? That's important. But in healthcare, recall is often the one that keeps people up at night. Recall asks, of all the patients who are in critical need, how many did our model successfully find? A low recall score is profoundly dangerous. It means your system is literally failing to see people who desperately need help. Okay, so the model is built, it's validated, it's tested, it looks good on paper. Now it's time to deploy it in a real hospital. But the journey is, well, it's far from over because the real world is messy and it changes in ways the AI was never trained to expect. As soon as the AI is in the hands of real people, a whole new layer of risk shows up. Doctors, who are pressed for time, might start to just blindly trust the AI's recommendation without applying their own clinical judgment. Or worse, a model that was built to assess medical urgency could get used for something totally different, like insurance approvals, a purpose it was never designed or tested for. And this brings us to the biggest long-term threat of all, something called drift. The world just doesn't stand still. First, the patient populations themselves change over time. That's data drift. Second, the meaning of the data can change as medicine gets better. That's model drift. And finally, the medical treatments themselves evolve. That's clinical drift. Suddenly, a model trained on yesterday's reality is making decisions for today's patients. This is so important. You can't just launch an AI and walk away. It's not a set-it-and-forget-it solution. It requires constant monitoring, constantly checking its performance against real-world outcomes, and reevaluating if its logic even makes sense anymore. This isn't a one-time project. It's a long-term, ongoing commitment. And sometimes, a model just becomes obsolete. It needs to be retired. But if that process isn't handled carefully, you get this phenomenon called shadow AI. It's basically an old, unsupported, unmonitored version of the system that people keep using out of habit. And that poses a massive, invisible risk. So when you zoom out and look at the whole journey, it's crystal clear that building a trustworthy AI is a continuous life cycle. It starts with careful data gathering, goes through training and deployment, but then it has to enter this permanent phase of monitoring, reevaluation, and eventually a safe retirement. And every single stage holds its own hidden risks. Which leaves us with the final and maybe the most difficult question of all. When an AI helps make a life or death decision and something goes wrong, who's accountable? Is it the doctors who used it, the hospital that deployed it, the developers who wrote the code? As these systems get woven deeper and deeper into medicine, this is the question we all need to be